Hello, this is a video for the final argumentative exam. So most of my work was done by hand and just all of the programming was done in MATLAB. And because of the time, I'm just gonna be explaining quickly all of the exercises. So to start off, the first exercise was problems Newton's law of cooling and heating. So I'm gonna show you my process. So for this first problem, I had to get the analytical solution of this equation, but rearrange it as a function temperature as a function of time. So to start off with this process, I just rearrange all of this equation, t minus ta to the left dividing and dt to the right multiplying. Once this was done, I just integrated both sides. On the right, I can see it's just a constant, so the result is minus kt plus c2. And on the left, I just use substitution and getting the result of natural logarithm of u plus c1. As we can see, both of the sides have a c, so I'm going to move them both to the right. And because both are constants, I'm going to rewrite this as c3. Because we're looking for t, then I'm going to use the rule e to the power of natural logarithm of x equals x in order to isolate this. So both sides, I apply this rule, and now I get t minus ta equals uh, this term. And because it was an addition, I changed it to a multiplication using the exponent rule. As you can see here, e to the power of a plus b equals e to the power of a times e to the power of b. So I divide both of these terms, and I can see that this is also a constant, so I'm gonna call this c. As for the last step, I'm just gonna move ta to the right and get temperature as a function of time equals ce to the power of minus kt plus ta. Now to interpret the constants. So as I mentioned before, well, as you can see here, I mentioned before, we have the initial temperature that T0 equals 0. So we're going to use this as a way to find the interpretation of the constant. So I'm going to substitute T0 into the equation. So at T0 equals Ce to the power of minus K time equals 0 also plus Ta. Because of the rule that everything to a power of 0 equals 1, then we can just rewrite this as T0 equals C plus Ta. And solving for C, we get C equals T0 minus Ta. This just means that C is the difference between the initial temperature and the ambient temperature. So when C is positive, then the initial temperature is greater than the ambient temperature, meaning the object is cooling down. And then if C is negative, then the ambient temperature is greater than the initial temperature, meaning it's just warming up. And we can see this here graphically, where C is the difference. When it's cooling down, then the initial temperature is up here, the ambient temperature, and it's making this exponential function. And on the other hand, when it's heating, then we see ambient temperature on top, initial temperature on the bottom, and C is also the difference between both of these. Now, the application to a problem which was the aluminum rod. So this problem says that it's initially at 25 degrees, then it's placed in an oven at 285, and that at T215, the temperature was 105. So first of all, we have to determine constants K and C. So we have the initial temperature, ambient temperature, we calculate C, which is the difference between both of these. And now we place C into the equation. Now, in order to get K, we substitute the point. We have T215 equals 105. Now, our process, which is just placing both of the values, subtracting 285 divided by 250. And now using this rule, logarithm of e to the x equals x. Now we can isolate K, which the final result is 1.71 times 10 to the minus 3. And we're asked to write the complete mathematical model, which is just putting both values into the equation, and this is the answer. Now we're asked that after reaching 285, and then this aluminum rod is removed outside, then how much time will it take to cool down? So here we have new initial temperature, which is 285, ambient temperature 25, C, which is the difference. And we're gonna place these values into the equation. Now substituting with the temperature 26 on this side, we can isolate for T. So once again, we just subtract 25, divide by 260, use the same rule as before in order to isolate T, and we get that T equals natural logarithm of 1 over 260 divided by the K, and the final result is 3,251.86 seconds or 54 minutes. Now I'm going to show you the code for the next part, which is a MATLAB simulation of the analytical solution and the Euler's method. So to start off this, I just created a vector of time, placed the constants for both of them, k constant, and the solution, which is simply calculating C, and then calculating the temperature with the same equation as before. It's just calculating for the vector and just placing the values inside of it to graph. As we can see, the red is the heating and the blue is the cooling curve. And here I placed the points of all of the things that were said in the last two problems, which was the found last, the one t equals 26, then how much time did it take to reach there when cooling down? It was 3,251.86. Now the Euler's method, we use the same constant, a final temperature, and here it's very important, this dt, which is the time step, which is how much, with how many steps of time this vector is gonna be calculated in. Now here I just create both of these vectors where the values are gonna be stored, the initial conditions for each of one, which is just placing the first value on the vector, and here using the Euler's method, which is just calculating from the first value up to one minus the last, and just calculating that the new value with the past values. And it's the exact same equation as before for heating and for cooling. And as you can see, here is the result. Now that we're asked to show both graphs, we can see that clearly they're both practically the same. We can see them one on top of each other. It's just that the red and blue are the analytical results, and the yellow and green are the Euler's method. And we're asked to show like any discrepancies in the analytical and numerical results. So there are discrepancies if the dt is a larger. So here, because we have a very small dt, we can see that the numerical solution is practically the same as the analytical solution, but with a higher dt, we will have inaccuracies. So yeah, that's it. The dt is very important to calculate the numerical solution, which is just an approximation. So the smaller the dt, the better the approximation to the actual result. Now for problem number 2, which is that heating seawater with a high power electrical heater. And first we're gonna derive the temperature equation, a MATLAB simulation, and curve fitting. So to start off deriving this temperature equation, I just start with this equation, which is Q equals mc delta T. And well, I'm gonna look for a function of temperature in respect to time as well. So to get this, I'm just gonna divide by time on both sides. This equals to power on the left side, and then I'm gonna change delta T as TF minus TI. Now I'm gonna rearrange this by moving 1 over T times mc to the left side, and also Ti, gonna move it to the other side, and this gets us a temperature function, temperature as a function of time equals Pt divided by mc plus Ti. Now I'm gonna show you the MATLAB code. So for this one, I just placed these initial values with 100 watts, 0.8 liters of seawater, and other search values to calculate this. So here are the initial values. Here is the mass, which was calculated just like the liters divided by 1,000 to get the mass in kilograms, the specific heat, initial temperatures, the time of simulation. And as you can see here, using the same equation, I'm just plotting the vector in order to create this graph. And well, it's a linear equation. Now, in order to solve the polynomial curve fitting, I had to do a vector, which is this right here, which does m times u equals t. So I'm going to show you how I did this process right here. So first I made t a column vector, and I just created m by just placing t 5, well, to the power 5, 4, 3, 2, 1 to make the 5-degree polynomial function, and then the ones, and just solving the system by dividing m, well, solving the system with u, which is like this type of division. Then I get the coefficients, which are 6, And now then I graph this with dt, and I'm getting these results right here. And as you can see here in the results, most of the coefficients are zero or very close to zero. So this means that the degree polynomial 5 is unnecessary for this, and that the computer is like trying to tell us that the relationship between temperature and time must be of a lower degree. Like that's what it's telling to us. Now for problem 3, which is a thermal equilibrium in a calorimetry experiment. So for this problem, I'm told that 0.3 kilos of 20 degrees water into 0.750 kilos of a copper kettle and at 170 degrees. So I'm going to use the principle of conservation of energy first. So QW plus QC equals 0. I just derived this into the equation seen in class. So mass water specific heat of water times the temperature of water, the same with the copper. I'm going to expand all of these and change the delta T as TF minus TI. Now, right down here, I'm just going to factorize TF. In order to get it, pass all of the other things to the other side and divide it. And this is going to give us the equation. And for the result, I'm just going to be using all of the values given right here in order to get the final result of the temperatures between both. And because this temperature is 48.1 and it's below the boiling point of water, we don't need the latent heat in order to find like how it changed from liquid to gas. For problem 4, which is thermal expansion of a solid cone, I'm first gonna derivate this in order to get the expansion equation, which is right here, and then calculate the thermal expansion. So for this model, I need to prove this equation of delta volume using the formula of the cone. So for this, I just started with the initial volume, well, the volume of the cone, which is pi r squared h divided by 3. And I need to find the new volume after thermal expansion. So I created both of these equations, which is R equals R0 times 1 plus alpha delta T. And I got both of these equations with the linear expansion of, the equation of linear expansion, which is L equals L0 plus delta L. I just rearrange it to get this equation. Now I'm going to use this in order to get the new, the delta V. So the initial volume, I'm going to calculate with the same equation, just naming the R and the H R0 and H0. So as you can see here, the volume is 1/3 pi times the new, the difference in the radius and the difference in the height. I'm going to expand the terms. Well, I'm going to move R0 and H0 to the left. I'm going to expand this, and then I'm going to multiply and add up the terms that are alike. And as we can see, the delta t squared and delta 3 cubed tend to 0 because a delta t is very small. And when you square it or make it to the cube it, it's going to be a very, very small result. So we can practically tell that's a 0. So we're going to assume it's 0. And we get this final equation, which is 1/3 of pi R0 H0 times 1 plus 3 alpha delta t. As we can see, this equation that we get on the left is the same as the initial volume I mentioned before. So we can just change this to B0. Now expand these terms, and we get this equation. And since delta V equals V minus V0, then we can rewrite this as delta V equals 3 alpha delta T V0, and V, the V coefficient equals just to 3 alpha. So we can plot this into, place this into the equation, and we get the same equation as we were looking. So delta V equals B VO delta T. Now we're required to calculate the thermal expansion. So as we can see here that we're told the initial volume is 105 and the change of temperature is 250. So in order to do this, I just place this into the equation. I investigated, and before still is this value, just multiply by the initial volume and delta temperature. I get that the delta volume is this one, And to get the final volume, it's just the initial volume plus the delta volume. And that's just adding up both of these terms. And I get that it's 10.592 liters. And lastly, for the problem 5, it's the work done in a gas expansion process. So the first question is just asked to, like, if the temperature increases, decreases, or remains constant. I'm going to show you with the ideal gas law. So as we can see, this is the graph. A is down here, B is up here. And we can determine this using the ideal gas equation, which PV equals nRT. We're looking T. So T equals PV divided by nR. Because N and R are both constants, when we can see that T is only dependent of the multiplication of P and B. So as we can see in point B, the volume and the pressure are greater than in point A. So the multiplication of both of these terms is going to be bigger. So we can say that the product when it's B, it's going to be more. So this is an increase in temperature. And lastly, for the last question, the work done by the gas, we're going to get these values right here. And what I'm going to do is just calculate the area under the graph. So first, I'm going to look for the slope of the line in order to calculate the area underneath of it. So the slope is delta y divided by L delta x. I get this result, and I just plot it into the graph, which is y equals mx plus b. M is this result as we get, and we substitute the point 0.7, 1 times 10 to the power of 5. This point I substituted into the equation in order to get b, and b is calculated as 3 times 10 to the power of 4. And well, lastly, I place b and m into the equation, so I get this equation of the line. Lastly, I'm going to integrate this equation. As you can see here, it's from VA to volume A to volume B. So it's the integral of volume A to volume B. Because it's B is the integral is B squared divided by 2 of the same term, and the other is just a constant, so I place B. And lastly, just substituting both of the values, and in the end, the value that I get is 4,800 joules. So I think that was everything, and thank you for your attention.